Super. So we're going to kick off. We're going to start recording. Um, Welcome. This is a research computing tech talk. If you haven't been to one of these before, this is our sort of slot. We're trying to do it monthly at the moment, where we touch on interesting topics and techniques that computational researchers here at Leeds would be interested in. We've previously done this on topics around reproducible research. And last month, we were very grateful to have a guest speaker from the University of Sheffield come and talk to us about the tool Pre-Commit, which is a tool for managing Git hooks. And this week, or this month is February for the purposes of this talk, it's worth noting, we're going to talk about Rust. This talk's come from the fact that Rust is something I've been interested in for a little while. I haven't used it at all in work, but last month I went to a conference, the first sort of Rust language conferences in the UK for some time, and as part of that, I thought, right, I should finally get my act together and sort of talk about it with researchers. So that's where we're gonna start, and we're going to ask. Well, I'm going to try and answer and ask simultaneously this question today, which is why you should maybe think about Rust for research. So to kick off, I'm just going to introduce myself because you might not have met research computing before. You might not have met me before. I know we've got some people on the call who are from outside of Leeds as well. So introductions are important. So I'm Alex Coleman. I'm a research software engineer here at the University of Leeds. I'm based in IT services, and we are a central team of research software engineers who provide support to researchers who are doing computational research. And we're research software engineers, if you've not come across this before, is this profession looking to bridge the gap between researchers who are writing software and software engineering and the best practices and tools that are associated with that, so that we can help accelerate research that is built around software. My background's not as a computer scientist. I was a researcher here in cell biology. I then did some data science, and from data science I got interested in software engineering, and that's how I sort of ended up where I am as a research software engineer. I'm also a Software Sustainability Institute Fellow for 2023, and my specific project is looking at software security, which is something I will slightly touch on through this talk. Languages that I'm into. So my predominant background is as a Python programmer, mostly from that data science background, and the same for learning the R language as well. But Rust, I would say, is now one of these languages that I'm into. It's one that I use in my spare time, and I would say I'm at the sort of, I'm past beginner, but in the sort of tinkering intermediate stage, which is where you get dangerous. But it's a reasonable foundation, I think, to maybe talk about Rust to other people. So I've also dabbled in a variety of other languages, but I wouldn't say they're languages I'm into or I feel particularly comfortable with, maybe. So I'm going to just I'm going to define what this talk is and also simultaneously what this talk isn't. So what I'm going to do today is I'm going to introduce the Rust programming language and its features, crucially its features that I think are most important and most interesting. I'm going to try and give you a perspective on why I think it could be a good language for research, crucially, and people writing research software. But I'm also going to give you some thoughts about why it might not be the right language for your research. I'm going to do this totally by the BBC book and try and go straight down the middle, and leave it to you to make that final decision about whether Rust is right for your research or not. Also, to define what this talk isn't, so this isn't going to be a deep dive into the language. We are going to touch on some programming language theory topics because you sort of have to do that. But I'm not going to dive deep into the internals. I'm definitely not going to showcase all the features of Rust, mainly because I don't understand all of them yet. But also I don't think it's necessarily something I could go into in the sort of 40-minute slot that I'm aiming for today. It's also not going to be a comprehensive comparison of Rust to other programming languages. I'm not going to do a pros and cons list against every language. I am going to draw on examples from languages that I'm familiar with, but it's not going to be sort of comprehensive in that comparison. And crucially, it's not a call for you to write everything in Rust after this talk. Okay, I'm going to leave that decision to you as to whether you're going to even touch Rust after this talk. But it's definitely not me saying I think everyone who does research should write Rust from now on. Okay. So with that in mind, what's Rust? So Rust is a programming language. It's a compiled programming language that came out of the Mozilla Foundation, probably most famous for their web browser Firefox. And it's a relatively new language. It only reached its first stable version in 2015, and it sort of came out of a series of projects in Mozilla that were looking to build something that was highly performant, but that was also had certain safety features and security features built in. So Rust defines itself as a language with this emphasis on security, performance, and usability. And with this in mind, it was sort of initially popular in the sort of systems-based programming space. Defining systems-based programming is kind of interesting, but it's all the sort of tinkery stuff you don't think about, I guess. In particular at Mozilla, their use of Rust is within their web browser in Firefox itself. And we actually see now that what was found with Rust is that it's very, very flexible, whilst it was used in systems-based programming to begin with, and that is now applied to lots of different subject areas. And that's why I want to think about it in the research space as well. So let's dig into some of these features with Rust. So the first one, which really does get the top billing, I guess, is this idea of safety and security, and it's predominantly through the lens of memory safety that we're talking about here. So if you're like me and someone who comes from a Python background, you don't really think about memory safety because languages like Python and R, these interpreted languages, they leave memory management to something in the Python runtime, something we typically call a garbage collector. And so we don't have to think about memory safety. Okay, we don't have to think about this idea of this memory that I'm interacting with my programming language. What happens when I free it? I don't have to actually think about how I'm managing memory at all. That's handled for us within sort of the Python and R runtimes. Now, if you come from a C or a C++ background or a more low-level background, you're much more familiar with this idea that you can manually manage memory with your program, and you need to manually manage memory with your program. And that lets you do very impressive and sophisticated things with those languages, but it also leads to problems in the fact that you have to be careful about how you're managing that memory. And it leads to a whole variety of problems related to managing memory, such as double freeing memory, buffer overflow sort of issues, and all sorts of other issues with regards to how you manage your memory. It's difficult for us as humans to have to start to think about that as we write our programs. And so many of the security vulnerabilities that we see in software in the lived world relate to this issue with memory management, and the fact that in things like C and C++, it's a hard thing to do. It's a hard problem to solve. So Rust out of the box defines itself as a safe language because it implements a way of managing memory without a garbage collector, but also without sort of manual memory management, if you want it, which we're going to go into in more detail. But that's the first sort of top billing. It defines itself as a safe language when it comes to memory management, but it does so without things like a garbage collector. And because of that, we get impressive performance. Okay, I don't have a good benchmark to quote for you, but by and large, Rust, when it comes to speed, is about as fast as C or C++, potentially in some cases faster, and that's all because we are able to manage memory safety, but we're generating compiled executables. We're doing this on top of the LLVM compiler toolchain, which is a very high performance toolchain. And that leads to very, very impressive performance with executables. It's a strongly and statically typed language. And again, if you're coming from a Python or R background, static typing isn't something you're used to. We don't have to define the types of our data in Python and R. We leave that, and these are dynamically typed languages, so we don't have to think about that. That's determined at runtime. Whereas in Rust, we have to use types, and we have to think about what types are going to be used in our program. And from a personal perspective, once I started doing this in Rust, when I look back at my Python code, I want to add types to it. And you can do that in Python. You can optionally type things, but I really like types, and having to do it in Rust actually made me do it more in other languages as well, because it's much easier than to see in your code what things are and how those things, and understand how those things are supposed to behave. But in Rust, the type system is very, very important. It's how lots of these guarantees around safety are ensured. And also it allows for a variety of other very interesting features which the language is able to do, such as zero-cost abstractions. So zero-cost abstractions are this idea that whilst Rust is a compiled language that allows you to do things on a sort of low-level basis, there are a number of abstractions within the language that are available to you from the standard library that don't give you any cost at runtime if you choose not to use them, and will be as performant as if you wrote them yourself. It's an idea that comes out of C++, but it's a very nice feature because it gives you lots of abstractions already within the Rust programming language that perhaps in a language like C, you would have had to have manually written yourself, and these come out of the box with Rust. This is a funny one, right? If you've ever done any compiled languages, you're used to dealing with the compiler. One of the nice features about Rust is that the compiler is actively helpful. What do I mean by that? I mean that when we come to generate our Rust programs, as part of our sort of internal development loop, if we get something wrong, and we'll talk about the compiler in a bit more detail in a bit, Rust will actively try and explain to you why it didn't compile, okay? And it'll point out in your code specifically where this problem was. And it may even suggest a fix for you. The interactions, I mean, I've compiled a couple of languages whilst being an RSE, and the compiler messages you get out of Rust are something completely different to anything I've ever experienced in things like C or Fortran. It's a very different experience, and it's helpful in a sort of weird way that you're not used to, I guess. It also has what I describe as a modern tool chain. So Rust, being a relatively modern language, has learned some of the lessons from other languages about what tools you need to use that language. And again, I'm going to talk about this in more detail, but it comes with things like a build system, a package manager, a version manager, a linter, all out of the box by default. You don't have to go and get those as third-party packages. And that's quite different to things like C, where those things aren't available out of the box. And it picks up on ideas that you might be familiar with in Python, where you have, pip as a package manager that comes out of the box with Python. But for the experience with Rust is you get all of these things sort of out of the box, which is very, very satisfying because you don't need to reach for, well, what build system should I be using or what linter should I be using. These all come for free when you use Rust. So I'm going to dig into some of these features a bit more. So memory safety. Okay, how does Rust achieve this memory safety guarantees without a garbage collector, but also without us manually managing our memory? So the way it does this is with a concept called ownership and borrowing, which is something that's drawn from sort of programming language theory. And this is defined through a set of rules that the compiler enforces at compile time, crucially. And the type system allows the compiler to enforce these at compile time. So the crucial rules of ownership are each value, each bit of data must have an owner in a Rust program. It can only have one owner at a time. And when an owner goes out of scope, then the value is dropped and that memory is freed. Okay, so reasonably simple rules here. But the idea that when things go out of scope, that memory is freed is how we're starting to accomplish this managing of memory without us thinking about it. So in Rust code, what does this sort of look like, or what sort of does this sort of look like? And I guess in this example that I've gone for here, I'm trying to highlight an instance of how ownership invalidation, I guess, works. So here we're defining a variable S1, which is a string. This is data that's kept on the heap, which is a data structure within our computers, that's as opposed to the stack. I could spend a lot of time talking about how strings are represented in Rust, but I'm not going to do that. And crucially here, we create the S1 variable that points to this data on the heap, this string that says hello. Then on line 4, I create S2, which is equal to the value of S1. Now that act of creating S2 and pointing it at another variable is passing the ownership of that data, of this hello string, to S2 from S1 and invalidating S1. So if I tried to use S1 subsequently in my program, S1 is no longer accessible, and this won't compile and it will give me an error. And it will say that a move has occurred and ownership has moved from one variable to another. Okay, I've pinched this directly out of the Rust book, and this is one of those concepts that is quite different in Rust to other programming languages, and one that definitely you have to take time to get used to how this is working. But one of the features that we have here is that once ownership has moved, we're invalidating old bits of data, and this again is enforced at compile time, but we might find instances where we're using functions. So in the example there, I'm just creating some variables and passing the variable to print. What about if we're passing variables to a function that we want, data to be returned from? Well, when we pass data to a function in Rust, we're passing ownership of that data to the function. Okay, so maybe you can see what might happen here because of that third rule is once the function goes out of scope, our data is going to be freed, it's going to be dropped. So to get around this, we use borrows to do this, okay, which is much like pointers, I guess, in other languages. But the idea is instead of passing the data itself, we can borrow that data with a sort of reference that's using the ampersand character. And this example here, we've got two functions. We've got a calculate length function that takes a borrow of a string and it returns an unsized integer. And we're just returning the value from calling the len function on a string. Now, crucially here, in the main function, we're able to create that S1 data and give the ownership of the string. And then to calculate the length, all we have to do is borrow, using the ampersand character, borrow the value in S1 and pass it to calculate length. And instead of of passing ownership of S1, we're just borrowing the value that's in it so that we can calculate that length. And that enables us to use both those values in the print call. Now, the compiler checks all of these things at compile time using a feature that's called the borrow checker. And this is sort of crucial to the model by which Rust is managing memory safety, because it's able to do these checks at compile time to make sure that these rules around ownership are being adhered to, and therefore it's going to satisfy these issues around memory safety. This sort of leads us on to concurrency. So this idea of using threads and how threads are managed in Rust. Rust defines itself as a language that offers you fearless concurrency. Okay, because one of the problems we get when we're writing concurrent code is the idea of a data race, is the idea of multiple threads writing to a piece of data simultaneously and overwriting data. The ownership model that Rust enforces at compile time also extends to threads. Okay, and again, it's using the type system to manage this, but this is its guarantee against data races. Crucially, is by using the ownership model so that the ownership of data that is passed around threads is done so whilst adhering to those rules of ownership. Okay, and that's very, very powerful. I don't write a lot of concurrent code, and indeed there's some very nice libraries in Rust that allow you to do things in parallel without even having to think about these things. But for people that I've come across who are using concurrent code, this is quite exciting to them because it avoids these issues around data races. Now, I put health warning here because crucially, I'm still not saying writing concurrent code is easy. Rust doesn't make it any easier than it used to be. It just helps protect us from some of the common issues we may have met in the past. So another feature that I really like, and now that I look back at other programming languages I sort of wish was there, is that Rust doesn't have a null type. Okay, we might have met this with lots of other programming languages where they needed a way of encoding that the value of something was none. It didn't have a type. We have this with the none or a null type. And we have this in things like Python and R. This often means that we have to remember to test if something returned by a function is the none type, okay? Because something can happen in the process of our functions that we're running, and it can return a none or a null value. And if we don't test for it, we don't realize, and then we get an error somewhere else. This is an error example in Python where you've tried to call an attribute on something that turned out to be a none type. And that can be very, very annoying. I've got some examples with R next, which also illustrate this. But crucially in Rust, Rust has an optional type, okay? And an optional type is sort of an enum, if you're familiar with that, a sort of enumeration. And an optional type can either have some value or no value. And Rust, by default, the Rust compiler forces you, when it come across these optional values, that you have to deal with the none type. You have to write into your code what would happen if the none type was to occur. And this sort of forcing you to consider error events is quite common within Rust. And it's great, okay? It makes us think much harder about what we're writing, and it makes us better think about what will happen if an error occurs in our code. So furthermore, we can think, we'll do an example now of how you handle these sort of, how you handle these optional types in Rust. With an example here with a sort of switch statement. So this is an example taken from R. If you're not familiar with R, you might be familiar with the idea of a switch or a case statement. So here in R, we're assigning a value. The value is what is returned from the switch statement. So the switch statement takes an input variable or an input piece of data, and it's going to match this to one of the options that we specified here, and it's going to return the value associated with it. So hopefully you can see reasonably logically here. I've got foo, I pass foo to switch, foo matches on foo here and returns 1. It's a sort of nicer way of creating if-else branches switch statements. Now, this is perfectly valid R, this top example, but you might wonder what happens if we gave the switch statement a value we haven't enumerated. So if we give switch something that isn't foo bar or foo bar, what happens? And in the bottom example, you can see if we give it magic, which I haven't specified a value for, we get a null type, okay? And when we get a null type, we now have to think about how we handle that null type in our code. This is also perfectly legitimate R code, okay? And people write code like this every day because they don't think that they have to handle the instance of where the switch statement takes something that they hadn't thought of. And that often leads us to writing tests further through our code to identify whether the variable is null, and in that case, we have to handle the error. Okay. Obviously, if you've been around this situation before, you might find that you can write a sort of catch-all arm to switch, but you don't have to, crucially. Okay. Now in Rust, you do have to write a catch-all. So in Rust, and maybe already I'm highlighting potentially a caveat of Rust, which is that we have to write a lot more than we did for R, but never mind. In Rust, this is what we would have to do. We would have to define a variable, which we've called foo in this instance, and we've assigned it to input. We're then going to capture a value called val, which is going to match on the input value. And the input value has to match one of the options we've specified here. Okay, so it's much like the switch statement here. Input is foo. It's going to look through the match arms and match on the one that it matches to. But crucially, in Rust, we have to include this section here, which is a catch-all arm denoted by the underscore, which says, what do I do in the event that input doesn't match any of the things I've specified here? Now, panic here just crashes the program. It's not very graceful. We could write something more graceful if we wanted. But by the very fact of it forcing us to have to think about this, it won't compile if I remove that catch-all arm, crucially. It will tell us we have to write something in the event that the match doesn't match. But the very fact that it's forcing us to think about this, to think about correctness, to think about how this program is supposed to behave if something doesn't go the way you intended, makes us write better programs, in my opinion. Okay, it makes us think much harder about the software that we're writing and how we're supposed to handle those error cases, and that's something that's very nice. And the more I go back to other languages as I have to write them, I crave the certainty of knowing that I'm going to catch errors in this sort of way. So that's a bit about Rust and its features. Okay, let's think. I'm going to try and convince you now what I think is great about Rust. Okay, other than maybe the things you've seen already that you really like. So I'm going to go back to the toolchain and waffle about the toolchain. So when I say toolchain, I mean those bits and pieces that are associated with a language but aren't necessarily related to it. Okay, so these are the things that surround the language that help us develop in Rust. But aren't necessarily the language itself. So Rust Up is the first one. Okay, so this is the official way that you would install Rust, and it installs the whole tool chain, so not just Rust and the standard library, but all of these other bits and pieces I'm going to talk about. And it also lets you manage the versions of Rust. So Rust has a sort of 6-weekly release cycle. I think it's currently on sort of version 1.67. Because the sort of core team is continuously trying to improve the language, and it aims specifically not to be a stagnant language. And Rust Up is there allowing you to pick which version of Rust you want to use, install newer versions, or revert to older versions, and that's really, really useful to begin with. It's not like having, for instance, if I, as a Python programmer, I manage my Python versions through a tool like Conda. You can use a tool like pipenv. You can just install it straight from python.org. But by default, we're sort of pushed to this official way to manage our Rust versions automatically, and that feels really nice. I don't have, a series of choices to make already. I just know how I'm going to get Rust and how I'm going to manage it with Rust Up. Then we've got Cargo. Okay, Cargo is the name of both the build system and the package manager in Rust. So if you're unfamiliar with the idea of a build system, things like C and C++, you need to compile your code, and you might orchestrate that with a tool like Make, or with GNU Auto Tools, or with CMake. And again, I've enumerated a variety of choices there that you might want to pick from. By default, we get shipped with a build system in Rust automatically through Cargo, and this is the predominant way by which you're gonna compile your code, you're gonna test your code, you're gonna build your documentation, you're gonna even publish your code. It's all done through Cargo. We very rarely actually touch the Rust compiler ourselves. We do everything managed through this application Cargo, and that is really, really nice. Already, I don't have to think about the build system that I need to pick to build my Rust project. I have one automatically. I also have a build tool that already knows about tests. It already knows about documentation, and it already knows how and where to publish my Rust code to a central repository. Rust by default already supports the idea of unit tests in your code. It already supports the idea of documentation through your code. So it has all these modern best practice ideas built into it so that you can write your code, write your tests, and write your documentation, build them all within the same build system, and not have to go and get a third party to do that. Okay, and that again is very, very powerful. To support these sort of best practice ideas around software engineering. Cargo also doubles as the package manager as well. Okay, so it's the way you're going to install dependencies through crates.io, which is the package repository for Rust. And you're going to manage those, and it will create a sort of project by project lock file that specifies the dependencies that you used. So for me, from a reproducibility perspective, put my research hat on here, the fact that we have a tool like Cargo for Rust that allows me to write my Rust code on my Windows machine, and Rust supports targeting all of the major operating systems, and all I need to do is make sure that you've got Cargo, you've got the right version of Rust installed through Rust Up, and you just run Cargo build, you can take the code that I've written here and reproduce it on all your devices. That to me feels very powerful. I don't have to give you a long series of steps to walk through. I have a lock file that specifies explicitly the version dependencies that are required for my Rust project. I don't have to tell you to go and get go and install Conda, for instance, and then install from my YAML, and then install from pip. I can do it all within this build system here. And that feels very, very powerful, and particularly advantageous within the scientific community, where we're really thinking here about how do we make things reproducible, but also how do we make them easy to reproduce between our colleagues. So we've got crates.io, which I've touched on before, which is this central package repository. This is much like PyPy for Python. It's much like CRAN for R programmers, npm if you do any JavaScript, all that sort of thing. You can publish your own packages here. And it's got a very big ecosystem of stuff. We're going to touch on some of those more scientific related crates in a bit. It also comes out of the box with a linter. I can't talk enough about linters. Maybe we should do a tech talk on it. But a tool that's going to suggest to you how to write nice code in that language. That's what a linter is. There's a whole bunch of them in Python. You can have Flake 8. You can have Black, which is a bit more exciting. You can follow. You can enforce PEP 8 in a variety of ways. But by default, Rust comes with a project-sponsored linter, which is Clippy, named after Clippy from the sort of Microsoft Word days. And that, again, comes out the box. Okay, you don't have to go and get that from anywhere else. That comes from sort of a centrally supported project. So that is very nice. As someone who likes linters to guide me to write nice looking code, having one out the box is really nice. Some other bonuses. So the joke is you should rewrite your code in Rust, okay? But one of the really powerful things about Rust is how it interfaces with other languages, okay? So you can add Rust to a C program, okay? And you can have C call to Rust very, very straightforwardly. There's a bunch of packages. C bindgen is a good example here that allow you to interface directly with C from Rust code or from C code into Rust. And this is how projects have started to move large C code bases into Rust, or start to adopt Rust into large C code bases. Because whilst the joke is rewrite it all in Rust, what you can do through Rust is, in a much more modular way, write this new feature that you want in Rust, but have it still interface nicely with your C program. And it's not just C, there's also good tooling for you to take a Python package, okay, that you've written in Python, but you've got this one bit of your code which could be more performant, and you know it could be more performant, and maybe you're feeling a bit good about Rust here. You could write that bit in Rust and then use a package like Pyo3 and Maturin to have your Python library call to Rust and run some Rust code under the hood to make it more performant. And the really powerful stuff around this is Maturin, which is the sort of partner tool to Pyo3, allows you to take your Python library that's calling Rust under the hood and bundle it and put it up on PyPy as a Python package so that anyone could install it as a Python package without having to install Rust. Okay, so you can ship Python code that calls to Rust without having to have your end users need Rust at all, and that feels very, very powerful for those of us that like Python and like the flexibility of Python, but know that in some cases we could do with something a bit more performant under the hood. The same can be said for R. So if you're an R user, I'm preaching to my own knowledges here, right? I'm doing R and Python, but I know it's the case for other languages too. But if you're an R person and you, again, have that problem, you want something to be a bit more performant, maybe you've written some C++ before, because R famously loves to interface with C++, you could do it with Rust if you wanted to, and you could get those memory safety guarantees through Rust in your R code for that performant bit. So this ability to interface with other languages works really nicely with Rust, and it's a very common thing that we're starting to see. And I imagine if there's another language I'm not talking about here that you're interested to know, does it interface with Rust? It probably does. This isn't to be overlooked, okay? So there is this thing that the Rust has a great community, okay? And that's sort of a weird thing to define for a programming language, okay? It's a technical tool that we want to use. What is a great community? But it sort of really does need saying that the resources around Rust that exist on the internet, the channels where you can talk to other people who are developing Rust, they sort of pride themselves on this openness and encouraging nature for people who are learning, who want to learn, and who are using the language and want to share what's going on. So there's a couple of things here. I mean, it goes without saying, if you're interested at all peak today, you have to go and read the Rust book to begin with. That is where everyone starts off. That is a book that was written by some people who are related with the Rust project. That's a sort of zero all the way to the advanced topics of Rust, and it's very, very good. It's all free online, and it's very good to go through. You're not going to go through it in one sitting though, so just take your time with it. I still haven't finished it, if I'm totally honest, but I've got a reasonable of the way through, and that's a really great entry point to the language. It shows its features, it demonstrates how you use it, how you write nice Rust, all that sort of thing. There's also a whole bunch of additional books that have sort of come off this project. So there's books about how you write Rust for WebAssembly. There's how you write Rust for embedded systems if you're interested in embedded programming. There's all sorts of stuff out there. This Week in Rust is a weekly email newsletter, which again brings community updates about what's going on, but also highlights blog posts where people have submitted showing how Rust is being used out there as well. Then there's this whole bunch of sort of communities. So there's a Reddit Rust, there's a Rust Discord, there's a Rust Zulip, and these are places where you can go and interact with people who are both using Rust but also members of the core team who are developing Rust, people who are working on the compiler. And it sort of prides itself in the fact that it's open and you can go and speak to people about these things and understand more. I would say for this talk, I did ask on the Rust Reddit what I should include in this talk, and I've tried my best to include as many of the topics as suggested, both from the people who said Rust is good for research and the people who simultaneously said, "Oh, I don't think it may be right for research as well." I will put a link to that at the end of these slides so that people can go and read that if they wish to in their own time and make their own decisions, because I definitely haven't included everything they said in here. So we've done what's great about Rust. Let's try for the things that maybe aren't so great about Rust. Okay. So sort of mirroring something I've talked about earlier, I'm going to talk about the compiler in what's not so great about Rust as well. So whilst the compiler is good and the compiler aims to be helpful, it's very, very strict. Okay. Ownership is something it will not give you a free pass on. It will not compile for all sorts of reasons. And this is part of your learning curve if you're going to learn Rust. Okay, you're going to learn to fight with the compiler. It's often referred to as fighting with the borrow checker. But that can be very, very infuriating. And I can absolutely see that there are people out there who try and learn Rust and get very, very frustrated with the fact that they just can't compile this application they're doing, and they can't quite work out why that is. Now, part of me thinks that the hardness of dealing with this process is a good thing. It teaches us good practice ideas, and the compiler is trying to guide us to the right answer. And whilst it is infuriating, it is trying to get us to a place where it's enforcing that correctness so that our application is working as it should. But it can be very dispiriting, and I think that's worth pointing out. Furthermore, and I can't say I've experienced this, I've never written a big Rust project, but for larger projects, I know that people say that the compiler is slow compared to C or C++. Okay, I think there's a variety of reasons probably for that. Some of which I know that the sort of compiler team are looking at improving. But for very large projects, it can take a long time to compile your code, which people have identified as a problem. Bounds checking. So, I mean, this is both a good thing and a bad thing to some extent. But you may be familiar in languages like C, when we index arrays, it is possible to index an array that doesn't exist in C, and we get what's called a buffer overflow. We get some random bit of data, and it's not particularly safe. And again, that's a significant security vulnerability, potentially. Rust, because of safety, implements this idea of bounds checking. Okay, and it does this at runtime, and it introduces an overhead at runtime because of this, because it's adding this additional bounds check. So that is something that is worth being made aware of. It's something I didn't really know, if I'm honest, until I started preparing slides for this talk, but I think that's worth something to be aware of. The learning curve. So I've drawn a pretty rubbish paint diagram here, but what I'm trying to convey to you is it is a difficult language to learn. Okay, I'm someone who learned Python, who learned R to begin with. Those are languages that let you write things pretty quickly and run them. Okay, Rust isn't quite like that, and it feels comfortable to begin with, but then you sort of crash into ownership and borrowing and how you're supposed to think about that in a way that you haven't thought about that before. In Python, you just create variables here, there, and everywhere. In Rust, you have to start thinking about how you're managing those variables. Okay. And so it's hard. Okay. I think it's a good hard thing though, because you learn a lot on the way, and often the hardest things we learn are some of the best things we learn. Okay. But you can't. But for researchers, and again, this is maybe a drawback, is this is an impediment to you. All the time that you spend not doing your research is time that needs to be fruitful. And if I'm suggesting that you should just drop everything and learn Rust, and it's going to take you a long time to learn, and I've already told you it might be infuriating in places, you may well just think, "Well, I could have just written this in Python and it would have taken half the time." So it's worth being aware of the fact that it is hard. And there are good resources out there to teach you, but you are going to have to go through a period of hardness to get there. Okay. So good bits, bad bits. What is Rust? Rust for research. So for me, these are some of the reasons I've distilled why I think maybe Rust for research. Okay. Firstly, and I talked about this already, but the fact that the tool chain is designed in the way it is makes it very, very easy to distribute our code. Okay. It makes it very, very easy for somebody else to take my Rust code and to compile it. Okay. On a different operating system, on a different platform. And portability of our code is a really big challenge in research. And there are all sorts of tools out there for how we do it in different domains. And I just think the ease of which you can do it in Rust is a significant advantage. Okay. It abstracts lots of the issues around building code away to some extent. It's great for performance critical code. Okay. It's as fast as C and C++. We don't have to worry about memory safety issues. Okay. That if you are developing research software that has to be performant in that way, this feels like a really good choice for that sort of code base. Okay, you need to give me some pretty good reasons why you should do this in C or C++ when a tool like Rust exists, if you have had problems in the past with regards to how you manage memory, in my opinion. And this is why we're seeing major corporations adopt this for various things. We're seeing this adopted by the big cloud vendors. We're seeing Microsoft look at integrating Rust into into the Windows operating system. The ability to now write Linux kernel modules in Rust. This safety guarantees around this stuff is a big deal. And if we're writing performance critical research software, we should be thinking about this too. There are lots of resources to help us learn. Okay. I think this is an advantage for us in research. Often the way we learn is through resources, and often the resources we try and learn things are scattered around the place. Okay. I'm not saying Rust has sort of a central list of reading lists, but by default it has a text you can go to that is officially sponsored to learn the language, and that feels like a really good start for these things. The other point at the bottom, and again is worth thinking about, is all of the code we generate, all of the code we run, all of those CPU minutes we spend on the HPC are spending finite resources in a time where we have to think about net zero and all those sorts of challenges. Rust, by actively forcing you to think about memory, by not having a garbage collector, by introducing us to low-level concepts and also being more performant, is a better use of resource. Okay, and that means that we will use less memory, we'll use less CPU time to run our research. So from a environmental perspective, there's a reasonable case here to think about whether you could use Rust for your research to write greener code, as it were. Okay, and there are some pretty crazy benchmarks, frankly, of people who've taken applications which they've then moved to Rust and reduced things like their memory footprint by 700%, and they've increased their runtime by sort of 50% as well. So the performance gain you get here isn't just about performance potentially, it's also about the use of resource that your code is doing too. It's also already happening. I'm not talking about you moving into this domain and then just building the bits from the bottom up. There's a couple of projects I'm highlighting here, which I think definitely need calling out. So we have Polars, which is this high performance data frame library. It's written in Rust. It's also got a Python wrapper. You can use this in Python and it's all working on Rust under the hood. There's NDArray, which is a crate, which is a Rust package for n-dimensional computation. Associated with that is n-dimensional linear algebra implementation, so you can use BLAS and LAPACK with these. Bioinformatics, there's a bio crate for common bioinformatics algorithms. In the Rust Reddit thread that I had, an academic from the States came in who is a bioinformatician and said he really thinks Rust is the future. It's what they're using in their lab for a lot of their bioinformatic analyses. So this is already being adopted in some research circles. Rust support for machine learning is as an active area of development. It's not sort of as mature as other languages, but it's definitely getting there. There's MPI bindings exist for Rust for you to write MPI code. That's message passing interface for sort of the high performance sort of parallelism. And general purpose GPU support, again, is an area of development in Rust. It's definitely not as mature as in other places. It's not quite where it is in things like C++ and Python, but I feel confident it will get there in the next year or the next year or two. So there's already a reasonable amount of work in this space that relates to research already. So it's not that we have to move into this space and build all of the building blocks we've met in other languages from the bottom up. Do you have to rewrite it in Rust then? Here's my answer. Crucially, what I want you to take away from today is no, not really. Okay, you don't have to rewrite it in Rust. Okay, you should think about it, but I definitely don't think you should rewrite everything in Rust. That's not what I'm trying to say. I'm saying that Rust has some really powerful features that you should perhaps explore for your research, and you should definitely consider it. Okay, and in particular, Rust might not be right for your research, and you need to consider this first too. Okay, so learning the language is hard. Okay, and as we've talked about already, time is of the essence with research, and all the time you're spending learning is time you're not spending doing your research, and so you need to balance that off, and whether you need it. You also have to make the decision about this trade-off about safety. Okay, is safety a big problem with the code that you're writing already? And versus the speed at which you're developing it, we've already talked about the fact that the compiler is very strict. Is that trade-off worth it for what you want to do? Okay. Just today, we had an academic talk to us about how they didn't need to write C++ code for some of their work because one of their students had come to some training that we did, and they had been able to write it in Python using the number just-in-time compiler, and it was just as performant as C++. So maybe you don't need to do that trade-off if you can write something as easily in Python, just using a just-in-time compiler. You've also got to ask yourself, is moving to Rust sustainable for your research field and group? Okay, it sounds great. I'll be the first to admit, I'm a bit of a magpie. I like shiny new things. But is it sustainable in your group? Are you going to write something in Rust and then leave that group and no one will be able to use it ever again? Okay. And is that the same in your field? Is your field something that's mostly sat in one language or one domain, and therefore moving it all out is going to be kind of difficult? Now, I salute you if you want to be a trailblazer, but you've got to make these assessments in the time that you have available. And again, I know lots of researchers enjoy the interactive programming experience of things like Jupyter and R Markdown, and that is not something that Rust offers. Okay, it's a different development experience to that. So if that's the way you do your research, or if these are questions you have to and ah about, then maybe Rust isn't necessarily right for your research, and you need to consider these when you're thinking about what to do next. So that pretty much brings me to the end of this talk, where I've tried to introduce Rust to you. I've tried to be nice and balanced and give you the pros and the cons. For me, I think to some extent this is going to be the future. Definitely for this performance code, this move towards this sort of memory safety model is very, very interesting. And I think we will probably see a move in the sort of next sort of 20 years where things like the option of writing C and C++ code is sort of removed by the fact that this sort of language exists. Because why would you, when you know you can do something as performant in a language that guarantees safety like this? And I think us as researchers need to think about that and be aware of that, and think about whether this is relevant to our research as well. So there's the question that I'm going to leave with you about whether Rust is for research. If you are interested, at the end of this, there are a couple of things you can go and check out. There's some more. There's also some more talks and some more things you can read at the end. And other than that, thanks for listening, and I'm happy to take any questions. I'm going to stop the recording now as well.